Alright folks, let's demonstrate what all interesting things we can do inside a circle. Here we have used a geoboard together with a bunch of rubber bands to demonstrate some kind of an experiment and geometry of circles. So I've made a circle on the outside. You can repeat it at home. At the same time, I've used a rubber band to connect the two edges, right? So these are 2 points on the circle, and this is the center of the circle. Here is the center of the circle. From the center, this band goes all the way to one single point on the circle. Therefore, the length of this is equals to the radius of the circle, right? Any point on the circle has a distance of radius r from its center, and so is this point. This point is also at a distance of r from the center. So here we have some form inside the circle where the radii are making a form, right? Now I'm going to connect these 2 points with a straight line. Any straight line connecting 2 points on the circle, be careful, those 2 points should be on the circle, is called a chord. The chord of a circle is any line, any straight line connecting any 2 points on the circle, right? So question for you, is diameter a chord? You go to answer it yourself. Next question for you, is radius a chord, right? So the definition of a chord is any straight line connecting 2 points on the circle. All right. Now, interestingly, this chord has a length, let's say L, and the radius is R. So what do you see here? It sort of forms an isosceles triangle. Why? Because these two sides of this triangle, let's call this triangle as triangle OAB. So the triangle OAB, where A and B are points on the circle, OA is equals to OB is equals to the radius. Now draw a perpendicular line from the center, and the perpendicular should be to the chord AB, and let it intersect the chord AB at a point L. That is the point of intersection. Obviously this perpendicular will also meet the circle at some other point, but I'm not concerned about that point. Let's call it L, where it intersects the chord AB. Now you have two triangles, triangle OBL and triangle AOL, right? These triangles share the same side OL. The length of the side AO is equal to the length of the side BO is equal to the radius of the circle, and because I have purposefully drawn a perpendicular, the angle here, both angles are 90. So from RHS, these two triangles are similar, and because the ratio of the similar sides is 1, therefore they are also congruent. That basically means that AL should be equal to LB. Therefore, any perpendicular drawn from the point O to the chord AB, so a perpendicular drawn from the center intersecting the chord AB at any point L will divide that chord into 2 equal parts. This is exactly what we've proven here.